my name is Dana Golden. Today we're finally getting into real environmental economics. Thank you for sticking with us to get to this point. And now to our regularly scheduled programming. So we start off by providing some vocabulary terms. So we have a shared vocabulary and a shared language with which to discuss environmental economics. Ambient quality is the quality and quantity of pollutants in the environment. So ambient quality is the current level of concentration of CO2, carbon dioxide, just any pollutant in the air. Environmental quality is the state of the natural environment, visual and aesthetic quality. Residuals are material left over from production and consumption. So once you make things, very important, I'm sure all of you know this, but once you make things, those things end up somewhere. Plastic gets thrown in a landfill or gets thrown in the sea, and you have to live with that. And when you consume things, those have consequences. In most of economics, we ignore residuals. We just say, you make this thing, and it just ends up being a thing. And it's used forever. Here, we explicitly, in environmental economics, are thinking about what happens after the consumption decision. Emissions, the portion of residuals that is placed in the environment. Recycling, the process for turning some of the residuals from consumption to be used again. Pollutant as a substance that you release in the environment and lower the ambient quality level. And then damages are the negative impacts from pollution. So here we have a demonstration of how you can mix multiple types of emissions. You have different sources, source 1 through n. These go into production, they create residuals, and then there's some sort of residual handling at each level, and then each of them create emissions to destroy the natural environment. They go into land, air, and sea, lower the ambient quality of land, air, and water, and then they create damages to humans in the ecosystem. There are real consequences to pollution, both to humans and non-humans. And there's a real cost to pollution that a lot of people think, it's just nice to have a healthy environment. No, it will cause real economic monetary damages if you don't have one. So you can have different types of sources, point and non-point. So the source is the location which the emission occurs. It can be local, regional, or global. And a point source is pollution that comes from a single identifiable source. A factory is a good point source. You could also have maybe a farmer that's using a lot of nitrogen that's running off in a local river. Non-point source, this is pretty common and very difficult. If you have a highway, you have a lot of different potential sources. If you have like a river that's polluted, you might say, well, here's the farm, but further upstream, here's the factory, and then here's the natural gas plant. And it's not clear where is this pollution coming from. So really a lot of this work, we're not going to talk about point sources and non-point sources a lot in this class, but a lot of the difficulty of improving the environment is you can't point to one person and say, hey, you guy, knock it off. You can't tell him to knock it off because there's no one him. There's like thousands of people doing things individually. It's a collective action problem. And one of those thousands of people is Elon Musk or Mark Zuckerberg, and they just happen to own lots of planes and lots of AI facilities that produce a lot of emissions, but together they're all non-point sources, and it's a bunch of people doing things individually, creating a problem. So here's point sources and non-point sources. Think of factories and vessels, and the non-point sources, roads, development, farms, cities. Farms can be point sources as well. If you have a large enough one, you have a lot of factory farming in some parts of the country. Particularly if you think about sugar down in Florida, there's a lot of factory farming. But you have non-point sources. It's really hard to stop pollution from non-point sources and to control it. So lifecycle analysis is one of the strongest tools in an environmental economist's arsenal. It's a big part of what allows us to do our job so that we can think about the costs and benefits of things over the entire stage of production. And this allows us to say we know that electric cars are better for the environment than gas cars. We'll talk about this a little bit later in the class, but it's not actually that clear that electric cars are better than gas cars on its face. Of course they are, but actually there is a turning point because electric cars are more intensive on the front end. So lifecycle analysis is a method to assess the environmental impacts associated at all stages of the product's life, from raw material extraction to disposition. So you have several key stages: raw material extraction, manufacturing and processing, transportation, distribution, usage and maintenance, and end of life. So you have to track this product all the way through to the end of life to see at every stage what are the emissions created. A big issue right now is if you think about offshore wind, you can't recycle wind turbines. No one knows what to do with wind turbines at the end right now, which makes the life cycle analysis a lot trickier than it will be once we figure out what to do with wind turbines, which, by the way, don't have that long of a life. They're only 20 years of life. So life cycle analysis helps identify and quantify environmental trade-offs and impacts to make informed decisions. And now policymakers, businesses, and consumers evaluate the real environmental costs. And a good example is comparing plastic and paper bags. I have a big bone to pick with the state of New York. The state of New York says that, you've got to have a reusable bag. You've got to have this... You've got to have paper bags, but if you don't want to have paper bags, we're going to charge you, or we want you to have these reusable bags. Actually, reusable bags require a lot of uses to be better than just plastic or paper bags. And, there are other effects of making people use reusable bags that aren't often thought about. It's harder on people who are commuters and who don't run cars. So it's not always simple to decide that one thing is better than another. Plastic bag, there's a very low manufacturing energy use. There's a high pollution from the raw material extraction, and there's a long decomposition period. Paper bags are much harder to manufacture. They use renewable raw materials. You don't necessarily have to worry about running out of trees. I mean, you shouldn't cut all of them down at one point, but you can get them back. And they biodegrade more quickly. But interesting enough, plastic bags actually have a lower environmental footprint often for single use, whereas paper bags are more sustainable when you use or dispose of responsibly. So often you'll see a lot of these trade-offs that you have to think through when thinking about which one is more effective. I don't know that this example is true. I think this is a better example comparing plastic and reusable bags. But I think the same analytical analysis can be done sometimes for plastic and paper bags. Here's a similar analytical analysis from a textbook I use for my other class, Sustainability and Economics. And this is a paper versus a polyurethane cup. So you think about, what goes into creating the cup, how much water goes into creating the cup, what is the emissions, water effluent emissions, what are the air emissions. You think about every result of creating the cup, and then, obviously it's almost impossible to deconstruct a polyurethane cup. It takes forever. It's not environmentally biodegradable. And it adds a little bit of mass to a landfill. So you have to think about these things when you're thinking about which one is really better. And you have to work through every stage of the development. Another example is electric vehicles. We talked about a moment before. Electric vehicles are much better for the environment, but if you only drove your car once, it wouldn't be better for the environment. It's a there's a turning point, there's a break-even point where an electric car becomes better for the environment. But fortunately, the break-even point is pretty quick, and it's pretty rare that you wouldn't drive an electric car enough to justify the emissions compared to a gas car. So a good thing to think about, you've probably heard of the CAFE standards, which are the fuel efficiency standards put in place by not the Environmental Protection Agency. The Environmental Protection Agency has its own fuel efficiency standards. This is put in place by the Department of Transportation. And there are actually two different standards for how we can think about the emissions. So actually, this is the difference between the CAFE standards and the EPA standards. The CAFE standards are tank to wheel. So when you hear fuel efficiency in terms of the an electric car or a gas car, you'll hear miles per gallon, and you'll hear, well, this is how much gallons goes in, this is how far the car will drive. That doesn't at all account for the total cost. The EPA tries to account for the total cost by including both from well to tank and from tank to wheel. So they look at everything that goes into the production of the gasoline, everything that goes into the or from well to tank, everything that goes into the production of the resources. And when you just have tank to wheel, you miss a lot that goes into the car. So now we're going to talk about the Malthusian Trap. Thomas Albert Malthus was one of the first economists. If you notice, he starts at 1766. About 10 years later is when, I believe, Adam Smith publishes an essay on the causes of the wealth of nations. So if you think Adam Smith is really the first economist, and then Malthus and John Stuart Mill are the next generation when you really see economics get started, well before Marshall and Samuelson, and really the formalization, mathematization of economics. And Malthus is really the first demographer. And in 1798, he publishes an essay on the principles of population. The basic idea is that population growth was growing faster than the food. You might have heard about this in AP Human Geography. You might also have had this worry at some point, is that there's going to be too many people and we won't be able to feed them all. And this can lead to really strong crises that can limit the population size. Pre-industrial societies experienced cyclical period of population growth followed by collapse. So for a long time, it really did look like there were firm rules governing how much a population could expand before it became disastrous. But then agricultural advances, particularly the first agricultural revolution in the second agricultural revolution in the 1800s, which alleviated pressures but did not break the cycle, but also the Columbian Exchange, the second agricultural revolution made things work, and then finally the Green Revolution in the 20th century. This was a really important start of environmental economics, because it's the start of thinking about non-renewable resources and sustainable systems, but it's also a big story in the history of economics, because it's the use of demography to analyze the economic system. So there's some assumptions of the Malthusian model, and think about these assumptions and think about, well, I'm telling you, why don't the assumptions hold, and how does that break the model? In this case, this is a model that we know is broken. We're all still alive. We've gone to 8 billion plus, I think, going on like a lot of people. And so population did not grow exponentially. It, slows down eventually, even in the absence of resource constraints. We've actually seen slowing of population growth lately. Another assumption of the model is that resources grow linearly because there's not enough land and technology. So think about Malthus is making a statement about the demand and the supply. In particular, he's making a statement about the production function that turned out was not true. But it wasn't totally untrue because the production function changed. You had more resources that came through the Columbian Exchange, and you also had the development of better technology. So when population exceeds resource capacity, per capita income declines, and then declining income leads to increased mortality and a worse world. So according to the model, population growth rate is proportional income per capita minus subsistence level. So as you have more population growth, suddenly you have a poorer population. And then there's this Malthusian trap. You have this idea that eventually there's going to be so much food required, not enough food produced, it's going to be a trap. We're all going to die. It's going to be hard. Such a rough life. What actually happened? You thought for thousands of years we couldn't get it up. We couldn't take off as a humanity. And then the Industrial Revolution happened. You saw massive production of agricultural goods in Europe and beyond, and suddenly food supplies grew. So an interesting feature of this is that we can also talk about this in terms of a development story. And I want you to think about, and we'll come back to this later more formally, the environmental Kuznets curve. So there's actually a really strong growth story and a positive story about environmentalism, in that as economies develop and as GDP per capita gets better, you see the environment start to worsen. This is especially true in rapidly industrializing societies. If you look at Manchester in Great Britain during the Industrial Revolution, you read a Charles Dickens novel, you read Coketown, not Coketown, you read Hard Times, and you look at Coketown, that's Manchester. It's just not a fun place to live in, and it's very hard. They're turning the birds black. When I say they're turning the birds black, I'm referring to they're changing the genetics of the birds so that they become genetically more predispositioned to have a different color. And it's not a good thing when you're changing the genetics of your population because there's so much pollution. So yeah, you hit Manchester. This is where a lot of countries in South America and Africa, the developing world, are right now. And then you hit a turning point and environment improves. Interestingly enough, you look at where China is right now, the environment's pretty bad, but it's starting to get better because when GDP per capita goes up, you see this real development of a demand for better environment and also efficiency that provides the wealth for economic growth and for a better environment. So that's the Kuznets curve. I'm going to leave it here, and then we'll pick up with the final video of this lecture next time. I hope you have a great day, and I look forward to seeing you again.